Welcome to our second lecture on mathematics in the 20th century, mathematics as the language of science, mathematics as the language of reason, and the challenges to those notions that accumulated in the course of the 19th and early 20th centuries. At the end of the last lecture, we left mathematics in what could legitimately be called a state of confusion as to the nature of mathematical truth. It should be startling to the rest of us, as it was to mathematicians, that something that had been taken for granted within mathematics and within Western culture for so long could actually be such a problem, namely accounting for the nature of mathematics and the nature of mathematical truth, the basis of mathematical truth. So it is legitimate to say, without being guilty of much exaggeration, that there was confusion among many mathematicians at the turn of early in the 20th century, 1900 to 1910, 1920, about the fact that the formalists, the logicists, the intuitionists were duking it out, and there was no clear winner and a couple of pretty clear losers, even though the losers included some of the greatest mathematical thinkers of the period. Let me say that this confusion did not at all hamper the productivity of mathematicians. They continued then, as they have continued throughout the 20th century, to generate new mathematics at quite an astonishing rate. The body of mathematical knowledge, creative new mathematical knowledge generated in the 20th century, dwarfs the mathematics created in previous centuries, in spite of the fact that the 19th century was one heck of a century for mathematics, just as in the sciences, the 20th century overwhelms the accomplishments of the 19th, so too in the case of mathematics. So this confusion did not translate itself into intellectual paralysis, but it is a legitimate problem when you begin to lose confidence in the foundations of your discipline. In general, it is fair to say that mathematicians live with a peculiar unresolved problem, peculiar when we put it this way, and that is, what is the nature of mathematical objects? Do they exist independently of the human mind or not? Now, when confronted with the bald question, many mathematicians will say, well, no. As Hilbert and Brouwer said, mathematical objects are created by the mind. But on the other side, you've got what Eugene Wigner of Princeton in 1960 called the unreasonable effectiveness of mathematics in the natural sciences, which says that there's got to be more to mathematics than that. Well, so there's a branch of mathematicians privately will confess that most mathematicians do believe that mathematical objects exist independently of the mind, that we discover mathematical objects and their properties. We don't invent them. That we discover the triangle and its distinctive properties. And that leads to a problem. If mathematical objects exist independently of the human mind, how do we learn about them? Well, we don't learn about it from empirical experience because mathematical objects do not exist in the world. There are no triangles in the world. There are no mathematical triangles in the world. There are triangular bits of metal or wood or leather, but there are no mathematical triangles or circles or spheres or squares. So we can't have learned it empirically. The intuitionists say, I got you there. We have intuitive access to these objects. So if you believe that mathematical objects are invented by the human mind, you've got the miraculous effectiveness of mathematics in the natural sciences to explain. If you believe that mathematical objects exist independently of the human mind, then you have the problem of explaining how we learn about them. Are we born with them, as Descartes seemed to believe, or he believed that they were innate, or somehow are they revealed to us because God allows us access to the divine mind, as Augustine believed, the Bishop of Hippo in the fourth century. This is an unresolved problem in mathematics, and it has some connection to the use of mathematics in the sciences, but we're just going to let it hang for the moment because I want to focus on Gödel and Turing. In 1931, Kurt Gödel, prior to coming to America and becoming a member of the Institute for Advanced Study, which was created in Princeton in 1933, Gödel proved that the consistency and the completeness of any axiomatic system as simple as arithmetic, and remember, for Hilbert, arithmetic was the key to axiomatizing all of mathematics. You begin with arithmetic. Gödel proved that you could not prove the consistency and the completeness of arithmetic. And he proved that you could not do it using logical tools that were developed by Frege and Russell, a technique that he borrowed from George Cantor's set theory. So again, we see something about how science and mathematics works. He plucked out of Cantor's set theory a mathematical technique, which for those of you who have some mathematical training is called diagonalization. It has to do with the diagonal terms in a matrix. Now, he took this tool from Cantor's set theory. He took various logical tools that Frege and Russell had developed, and he used the self-referential paradox constructively to put together a proof that when you work your way through it is dizzying. So it's good to have some anti-vertigo pills nearby, but it's beautiful. And it's by no means obvious, but it is certainly convincing that it is provable. It is provable that you cannot prove the truth of all arithmetic statements within arithmetic. If you want to have an axiomatic system, fine, but you can't close it. You can only close it by having a higher level axiomatic system in which your arithmetic is embedded. But now you have to worry about axiomatizing that system, and since it's more complicated than arithmetic, it's going to be vulnerable to exactly the same problem. You go up to, no sense going up to that second level. It can't be done. So Gödel's proof, which is called the undecidability proof, Gödel's undecidability proof is a philosophical shock analogous to the discovery of non-Euclidean geometries in the 19th century, or invention, depending on your attitude towards mathematical objects, as I just ran through. This is, again, it's a kind of an abstraction that it's easy to toss off as just some ridiculously esoteric thing. And in fact, it has not had a great impact on subsequent mathematics, except in mathematical logic, where his proof technique has been extremely fertile. It doesn't change the overwhelming majority of mathematicians' attitudes towards their work, but it does show us that the formalist interpretation of mathematics is not possible, as the logicist wasn't. And most mathematicians, while recognizing that there's some truth to Brouwer's intuitionism, don't believe that intuitionism is correct either. Now, since those were the only three horses running in the race, and none of them won, was there a race? Well, that's a very philosophical question, but we certainly are left dangling with respect to the question of what is the nature of mathematical truth? Well, best not to ask, keep plugging ahead and using mathematics in this unreasonably effective way in which it continues, as we will soon see, to be extraordinarily fertile for describing experience, for predicting new kinds of experiences that no one had anticipated, in spite of the fact that we do not understand the connection between mathematics and reality. In 1936, one of the constructive byproducts of Gödel's proof was that a British mathematician named Alan Turing used Gödel's proof, incorporated Gödel's proof into a line of reasoning of his own in addressing the second problem that I told you about of David Hilbert's, which was the business of the effective procedure. Is it possible to have a mechanical decision procedure that if you step through it will correctly solve any mathematical problem that you're given? And for starters, any problem in arithmetic. So Turing proved that you could not do it, that no such effective decision procedure existed. That's the end of formalism. Hilbert's mathematics lives on, especially his contributions to multi-dimensional, in fact, infinite-dimensional geometries, which is a fundamental part of quantum theory. But his philosophy of mathematics is not defended by many people. There are some, but people who believe that they have improved upon it and they have patched up holes. But by and large, formalism, as Hilbert conceptualized it, was dead by the end of Turing. Turing, in order to prove this, and we're going to set aside the proof, it's in a paper called On Computable Numbers, which is readily available. Turing used as part of his proof an imaginary machine. He imagined the following machine, which would be an embodiment of a mechanical decision procedure. This machine is very simple, extraordinarily simple. It acts on itself in accordance with a set of instructions that are built into it. So the machine takes the form of what we would today call a read-write head and a long strip of tape. In fact, for purposes of this mathematical proof, it's an infinitely long strip of tape. The strip of tape moves forward one square. The machine reads it, sees what's written on it. It's very simple. It's either a 0 or a 1. It's not reading English sentences. If it's a 0, then it's got instructions. Well, if it's a 0, then move one box to the left. If it's a 1, move 2 boxes to the right, whatever the instructions happen to be. And then the instructions may say, change the 0 to a 1, advance the tape 1 unit, change what's ever written there. Right? You can get the idea. And using this conceptually extremely simple machine, Turing was able to do the mathematical proof. Now, if that's all, then it would not have been a big deal. But my guess is that even if you've never heard of Turing before, you have already recognized that conceptually Turing invented computer science. He invented the computer and computer science. Now, what Turing recognized was that his disproof of Hilbert's problem, his proof of the negative of Hilbert's problem, had as a corollary that given an algorithm, given an effective decision procedure, a machine like this could solve any problem that you gave it, for which there was an algorithm, an effective decision procedure. So what he proved was that there can be no effective decision procedure for arithmetic. But if you give me a problem and an effective decision procedure, so if you know in advance that this kind of a problem can be solved by following the following sequence of steps, this weird machine, imaginary machine, could solve any such problem. And that's what a computer does. A computer can solve any problem for which you can write a program. As long as you can write a program for the solution, the computer will come up with the right solution if all the bits and pieces are working correctly. Turing did not know that in parallel, in the United States, 2 different individuals, a very sophisticated mathematical logician at Princeton named Alonzo Church, and a European emigre wildly underemployed in New York City of the Great Depression named Emil Post, had effectively come up with the same ideas in the same time, and about the same time, within a year or two. Post probably the earliest, Church probably at about the same time. Eventually all of this came out. But Turing is the man that gets the credit. The machine is called a Turing machine by people in the computer industry. And Turing also, of course, could not know that in the immediate future lay World War II, when his imaginary machine would be converted into a real machine, a stored program, electronic digital computer, and that it would have the impact that it has had on our lives and, of course, also on the practice of science, since computers began to spread through society primarily in the 1970s and 1980s, society and research labs. Turing himself, during the war, worked on a kind of an analog computer that was used to break the code of the German High Command. It's a very well-known story, very famous story, the Enigma code. And he was one of the key players at Bletchley Park, which was the home of British Cryptographic Service, and they used something that is legitimately called a computer in order to keep up with the variations on the Enigma code that the German High Command used, so that they could consistently break the code and inform Allied High Command of what the Germans were, the instructions that they were sending out. After the war, Turing worked on the first generation of electronic stored program digital computers in England, and was associated with pioneering work on such computers parallel to the work that was being done here in the United States, and then in the early 1950s committed suicide in the wake of his prosecution and conviction for homosexuality. He was found dead in his room, and Snow White-like, there was a bite taken out of an apple. The authorities said that it was strychnine poisoning that was in the apple, and that's how he died, although in fact no autopsy was ever done, and he was being closely watched by British intelligence since his conviction, because they considered him to be an unreliable security risk. So without being conspiratorial, I won't say anything else except that his death seemed to be rather sudden and surprising, even though he was, of course, depressed about having had his lifestyle, which was rather flamboyant ever since his young adulthood, so stigmatized. So he was so stigmatized, and his movement so carefully watched. So Turing launched computer science. Now, I want to focus on a couple of aspects of the use of computers and the implications of computers, because I don't need to tell you much about those. We live with them all the time. One is the use of computer simulations in science. At the end of the 20th century, computer simulations were ubiquitous not just in the physical sciences and the life sciences, but in the social sciences as well. And this is another version of looking at mathematics as a surrogate for reality. We look in the computer simulations for clues as to what the real world is like. So we are, again, repeating this often intuitive conviction we have that mathematics somehow captures features of reality. And computer simulations being used by geologists, for example, to simulate what the Earth, the processes going on beneath the crust of the Earth, the mantle, the convection currents in the mantle that drive the plates apart, as we will see, the continental plates apart, as we'll see in a later lecture. This is all studied, because you can't get beneath the mantle. This is all studied in computer simulations, into which we plug a tremendous amount of data that's been collected by instruments, primarily from shock waves, from measuring the way shock waves spread throughout, earthquake shock waves spread throughout the globe. And then we construct these computerized movies that simulate what's going on, and then people study them and say, now I can see where I can do an experiment to test that. So you're looking into, now that's a mathematical construct. That computer simulation may look like a movie on your screen, but it's a mathematical construct. So that's one way that computers have influenced the practice of science across the spectrum, from physics to economics and archaeology, that computer simulations are what we turn to. They define, often the use of the computer in science defines what kind of a problem you will address. Because without the computer, you wouldn't even attempt many kinds of problems, because you couldn't do it. You couldn't process it. What would you do with 16 million events if you didn't have computers to process that data? How would you be able to find patterns that would allow you to identify the top quark, as we went through a couple of lectures ago? So the kind of problem that you address is influenced by having computers of a particular capability available to you. And in fact, one of the things that has happened is we can now avoid simplifying problems. We can address problems in greater complexity because of the computer, having the computer as an aid. Historically, you always had to simplify. I'll imagine that it's a weightless rope and a frictionless surface and so on. Now we can actually include as much complexity as the computer can handle. Second way that computers have been interestingly involved in our reasoning is, since the 1980s, and a famous theorem called the four-color map theorem, the mathematicians have been using computers as part of mathematical proofs. Many mathematical proofs are very complicated, and if you could run through hundreds of millions of calculations, you could resolve some point. Well, no one's got the time to do that, but a computer can do that. So you have mathematical proofs in which one stage is input to a computer, output from the Now, what kind of a proof is that? The classical term for a proof in mathematics is demonstration, from the word to show, Latin root to show. The idea of a mathematical proof was to show the line of reasoning so that anyone who followed it could see that the conclusion had to be true. That's why we do proofs. We don't just take some mathematician's word of it for it that X is true. Let me see your proof. Now, if a computer is one step in the proof and you can't check that, because no one's going to do the 300 million calculations, then what kind of a proof is that? What does a proof like that teach us about our reasoning, which is historically one of the virtues of mathematics, is that it teaches us about our own reasoning. So those are unresolved and perhaps unresolvable questions, but it is a fact that mathematicians, after considerable controversy in the 1980s, have adapted to some extent to the use of computers in proofs. What I want to turn to now, very briefly, is to talk about some developments in 20th century mathematics that have proven to be extraordinarily fertile in natural science. So in spite of all of these background philosophical confusions and issues which are not well resolved, it continues to be the case, whether you want to call it unreasonably effective or miracle, it continues to be the case that mathematics, new forms of mathematics, continue to be fertile in natural science. One of these, expression of this, is what is called, I think a little unfortunately, game theory. Game theory came to attention in 1943 with the publication of a book by the Hungarian émigré physicist, also at the Institute for Advanced Study in the 1930s, John von Neumann, who played a major role in the development of computers at the end of and after World War II, really the central role in computers as we program them, and played an important role in quantum theory. He's quite a polymath, a major figure in the Manhattan Project. In 1943, he and a collaborator, Oskar Morgenstern, published a book on the theory of games, which builds on work that von Neumann had started in the late 1920s and actually published on earlier, but it was in 1943, in the middle of World War II, that game theory began to send out shockwaves throughout the intellectual community because it gave a mathematical model of rational choice, a mathematical model of how to calculate what the rational decision was to make in a particular situation. Almost immediately, von Neumann applied this immediately to military tactics. And this turned out to be quite fertile in showing that commanders facing specific situations could calculate what the most rational choice was, what the highest probability positive outcome could be in different kinds of situations. Maybe the prisoner's dilemma is one example of this that's become quite famous, but the broad implications of game theory are that rational decision-making means making decisions consistent with this mathematical analysis of outcomes and the weight that you put on negative outcomes, positive outcomes. So that defined rational decision-making in the context of the war, quickly adopted by military planners, but after the war, it has become absolutely central to political science and economics, for example. Game theory is extremely influential in psychology, economics, and political science. We will, in subsequent lectures, be looking at late 20th century challenges to this notion of rationality. And in fact, the last few Nobel Prizes in economics, really a Nobel Memorial Award in economics, have gone to people who have argued that people's economic behavior is not rational in this way, and that doesn't mean people are irrational. It means that this model does not correctly describe what intelligent decision-making is, keeping the word rational out of it. But game theory has been extremely influential, and for reasons that I just mentioned. The second area that sounds also odd that we would be able to find any positive value from is a branch of mathematics created in 1951 by an IBM mathematician named Mandelbrot, who built on work that was done in the late teens and early 1920s by a range of mathematicians who studied something called self-similar algebraic curves. That means shapes, each part of which has the same shape as the whole. And he gave the name fractals to this branch of mathematics. Fractals are a branch of mathematics that studies the way that objects can be constructed when the rules for building them are to apply over and over again the same formula. Recursion, It's a very important idea that has become central to a number of 20th century sciences. I don't want to spend much time on fractals, and this may seem like a bizarre way to put it, but Pixar animation is heavily indebted to fractals. The increasingly sophisticated computer graphics that movie makers are capable of is a practical application of this extraordinarily abstract branch of mathematics, as I said, created as a distinct branch of mathematics in 1951 by Benoit Mandelbrot. Third area of mathematics that we need to mention is what is commonly called chaos theory, but really probably should be called complexity theory. Complexity theory is an attempt to describe mathematically systems, physical systems, that don't behave nicely. Systems that are turbulent and look chaotic. The weather is an example, is a classical example. And they're called chaotic systems, but if they were really chaotic, you couldn't describe them mathematically. If they were really chaotic in the sense that anything could happen next. That's not what chaos theory really means. Chaos theory applies to systems in which the evolution of the system over time is not predictable because of the sensitivity of the system to minute differences in the initial conditions. That a system, such a system is called nonlinear. That means that for a given input, there is a closely correlated output. Small input, small change in the output. Large input, large change in the output. In a nonlinear system, a small change in the input could lead to a very large change in the output, and a large change in the input might lead to a small change in the output. So nonlinear systems are much more complicated than linear systems, and it becomes, in fact, one of the characteristics of second half 20th century science is that we have become increasingly sensitive to non-linear and non-equilibrium systems. And perhaps the computer is what has enabled us to add this level of complexity to nature. I think it is of fundamental importance that 20th century life and physical science have shifted from the 19th century notion of equilibrium as the norm, and that whenever there's change in a system, the system wants to get back to the norm. One of the things that complexity theory, chaos theory, has shown us is that there are many systems that can remain on a non-equilibrium basis through a kind of self-organization. This was pioneered by the chemist Ilya Prigogine, who received the Nobel Prize in 1977 for his work on non-equilibrium thermodynamics. And it has important implications for life, because if this showed us that the 19th century idea of entropy is not a death sentence for the universe, that within nature it is possible for self-organizing systems to maintain themselves far from equilibrium by absorbing energy from their environment and transforming it in ways that sustain non-equilibrium. So that dynamism, change, is not a disturbance from the norm. Dynamism can be the norm. And when we reach the discussion of plate tectonics and geology, then that will become very clear when applied to the planet. There is one other area of mathematics that I need to mention, and that has turned out to be extraordinarily fertile for science in the last third of the 20th century, and that is something called network theory, which was, in its modern version, triggered by two Hungarian mathematicians who had been schoolboy friends, and Paul Erdős and Alfred Renyi. They, in a certain sense, started modern network theory. The important thing about network theory for us is that it is a theory of relationships. The nodes turn out to be of no significance. The structure of a network has properties independently of the relationship. And those properties are what are critical to the way the network behaves. Neural networks, gene networks, protein networks in cells, it is the structure of the network that has consequences for how proteins work, not understanding the individual proteins. When we start looking at and you can hear in this an echo of the many times I have pointed out how relationships have increasingly become the focus of science in the course of the 20th century. Not things and their fixed properties, but relationships as, in some sense, the underlying reality that sustains the universe. And when you apply this network notion to genes and to proteins, as we will see you need to do, then you begin to realize that this mathematical abstraction has considerable physical power.